what we have been seeing last time, last two lectures, is putting the Neutrino mixing in the framework of 3 Neutrinos. And so, 2 classes ago, we saw how to fit things when we ignore any complex nature of the mixing matrix. And then we saw how the solar angle is necessarily theta 1, 2, atmospheric is theta 3, and then we have this third angle which is called theta 1, 3, on which we have the little so just for that, not reactive. And in the last class, we saw what happens when we introduce equivariation. So we try to look at differences in the probability of, let's say, u e to mu u and u bar to mu. U bar to mu. So, particle oscillations and antiparticle oscillations, there is a difference. We saw that that is complex phase in the PLS. So, just to remind you what we have is. So, this is a standard parameterization that we are always going to talk about. This I1, Cal2, and Cal3 are so-called flavour phases, which never appear in any oscillations. So, we go on that. The rightmost matrix is this phi 1, phi 2, phi 3, another phase matrix. These two are Majorana phases, and although you may be able to observe them in some physical experiments, that later on, they will never play a part as far as oscillation happens. So for oscillations, although UPNS looks like this big thing, we only consider this purple part. Purple part is called as utility EMNS. It's not a standard notation, it's time of notation. But people sometimes call it simply as UPNS. This consists of rotation in 2, 3, complex rotation in 1, 3, rotation in 1. This is R2, 3, this matrix, rotation in 2, 3 plane. This is rotation in 1, 3 plane. This is rotation in 1. So as far as oscillation experiments are concerned, it's enough to consider this utility equivalence, which is this. So it's a big matrix. After going away the phases, we still have this matrix, which contains 3 angles, theta 1, 2, theta 1, 3, theta 2, 3, and 1 phase delta. So, in order to study neutrinos, our first aim, therefore, is to figure out what are the values of these parameters. So, we try to figure out what is theta 1, 2, 2, 3, 1, 3, and delta. There is one more unknown, which is the sign of delta n square atmosphere. Now, as far as theta 1, 2 is concerned, we know approximately how much it is for the experiment. Again, theta 2, 3, we know approximately what it is for activity. So, let's try to at least find some information about other angles which we don't know. And for that, now we have to necessarily go towards 3 Neutrino oscillations and see how to deal with them. So we saw today's episode. We saw that we can always write probability of conversion in a simple form. So if you are given the mixing matrix, UPMNS, all the elements, then you can calculate these quantities, these brackets, alpha, beta, iota. Then, if you know all the masses and energy, you can calculate this delta G. Delta n square 4 e, so you can put in delta G. Which means given the UPMNS matrix and the delta n squares, you can in principle calculate the value of the alpha. So this is very standard. Except that this is true only in vacuum. The expression that I gave is true only in vacuum, and that's because as soon as you enter matter, you have matter effects. Matter effects means that your UPMNS is going to change. Now we did something similar when we did 2 Neutrino oscillations. We added this potential term and saw how the mixing angle changed. So in the case of 2 Neutrino, So we had two neutrinos. We added matter, and then we could calculate the value of theta m and delta m square. But we had some. Now that you have three neutrinos, things are complicated because we have three angles. So three angles is simultaneously change and become something else. So the picture in the sense is a bit more complicated. So for example, this theta m was very simple. Diagonalizing proability is very simple because you have to solve the quadratic equation. Solve this secular equation is quadratic. You know what the answer solution looks like. So eigenvalues is very easy. When you go to 3 by 3, it's a cubic equation. So in general, the solution is cannot be written down in half a line. So therefore, we don't want to build into that. We do not want to take the 3 by 3 Hamiltonian and diagonalize it completely. Because that is going to be a very basic thing. You can do it numerically, but you will not get any deeper understanding of it. So we will follow another path and try to find how to do it. So what we are going to do today is the following. So first, I shall show you a technique of how to calculate oscillation probabilities inside matter with three neutrons. This is some technique that you all should practice a lot and know, because in the future this technique is essentially what's going to be used to calculate it. If you want to calculate any survival probability of mu, in the future mostly belongs to this so-called long baseline experiments. You start at one point, you go maybe 5,000 kilometers away, and then you just pass through the Earth and find what happens in the region. So for all the new big experiments, therefore it's essential that you have to travel through the Earth. And therefore it's essential that we try to see how to calculate probabilities when neutrinos pass through densities like that of the Earth. So this is a technique that so I will first teach you this technique, and then we talk about the so-called long baseline experiments, which is in some sense the future of this art of neutrino physics, which measures neutrino parameter angles, masses, gets to the physics. So first to calculation and then to applications and current. So let's see what the problem is. Let's say HF is our Hamiltonian in flavour basis, as usual. Which means you can solve Schrodinger's equation. It's simply I d by dt of this nu now is HF times nu. So problem is not difficult. Basically it's just solving this. For HF, we have learned how to write in terms of delta n squares and so on. Okay. So how do I get it? So see, it's easier to write the Hamiltonian in the mass basis. So let's first go to vacuum mass basis. So let's say the vacuum basis. Okay, write down the Hamiltonian. So this vacuum. So it basically will look something like m1 square by 2e, m2 square by 2e. This one can call as h. This part, Hamiltonian m square by 2. Of course, we know that common terms don't matter. So I will subtract n square by 2e, m1 square by 2e from all diagonal elements. This is equivalent to 0 m2 square minus m1 square by 3 and m3 square minus notation says that this quantity is 2 times delta 2 1. Remember delta was delta n square by 4e. Since this 2 is 2 times delta 2 1. This quantity is 2 times delta 2. So our Hamiltonian actual looks like this: 0, 2 times delta 2 1, 2 times delta 3 1, and here comes delta. So now we'll go to the flavor basis and see what becomes this Hamiltonian. So in the flavor basis, the Hamiltonian is 2 Hamiltonian in mass basis. That a simple basis observation. Flavor to mass to flavor is 3. So this is perfectly fine in vacuum. Now we are going to add matter potential. And matter potential we know essentially looks like some V charge current or electron and 0 elements. This part we just call as potential. Exactly what we had done in the case of Neutrino oscillations. Now it is going to work. That's exactly what you see in the logs. So the Hamiltonian is the U diagram plus V, where this H hat is this quantity which we just wrote down, and V is the matter potential. U here is this utility. I don't care about all the phases, throw them away. But it still has all these things, so it's a rather big matrix. So now with this U, I need to calculate the value of H. And it won't take me hard to convince you that if I really want to write down HF, that's going to be complete waste. It's going to give the force. I don't want to try to write it. However, the aim is this: to write down this U, calculate the product of this, add this V to it, and whatever I get in the hand. That's what I want to write. But if I do that, let's say by some means I'm able to diagonalize the matrix. So diagonalize the matrix, what happens? Then I find out what the eigenvectors are. Eigenvectors are the same as mass eigenvectors. Then I find what are the eigenvalues, which are the mass values in matrix. So once I find that, what can I say? So remember, when we did not have any matter, so what happens? I start with Neutrino state called as mu alpha. This mu alpha 0 was some summation of mu alpha I times Q. So I convert that into mass basis. At time t will be alpha I. Now this ui, it will have gained a phase, which is e to the power minus I. G. J times N. Okay, so all that this state does is gain of phase e power minus I epsilon J times N. That's not a big deal, simple solution. Now I want to calculate the value of alpha beta. So P alpha beta is going to be mu beta mu alpha. And I know how to do that, which is just summation. Since it's mu beta, this is going to be u star beta j times alpha j or minus I epsilon j times n. That's it. Now, so even in vacuum, this is what I was going to do. When I go to matter, all I need to do is instead of this u, I should calculate the element of u matter. And this epsilon j, instead of delta m square by 2m, I am going to do the eigenvalues. So which are the modified form. These are eigenvalues. Earlier eigenvalues were simply delta m square by 2a. Now they are going to change. So which means that once I calculate eigenvectors of HF, I know what is UN because mixing matrix essentially becomes the eigenvectors. Once I calculate eigenvalues, I know what is epsilon G. It's clear so far? So once I calculate these quantities, I know what to do.
Epsilon G is the eigenvalues of the flavor.
But eigenvalues are the same. Yeah. So how to write epsilon G is very simple. You take HF, you diagonalize. See eigenvalue. That's simple. What is how to determine this mixing matrix UN? And this perhaps you know, right? You have normalized eigenvectors and you put them in columns to get your U matrix. So in some sense it's like this. Okay? So what is this U matrix? This mu e mu v mu tau is um times mu1 and mu2 and mu3. So therefore mu1m, mu2 and mu3m, the three mass eigenstates dagger, are given by um dagger times mu e mu v mu3. So let's write down this 3 in terms of mu e mu v mu3. What does this mean? That this um dagger would be mu1m component 1, component 2, component 3. We are working in flavor basis. So in flavor basis, write down your mu1m, take as 3 components and write them down as a row. This will be um dagger. Dagger that you get that. This clear? I'm sure people have seen this. However, what needs to be taken care of is that this mu1m, mu2 and mu3m should be normalized eigenvectors. Essentially they are normalized because we want this u to be unit element. So basically what we need therefore is all these epsilon j, which are eigenvalues of HF, and these mu jm, which are normalized eigenvectors. This is what we are trying. So how do we do it? I already told you that if I get a random 3x3 matrix, I am going to have a hard time calculating its eigenvectors analytically. So what we do is we use perturbation technique. Perturbation technique means the following. We don't solve for the HF itself. We solve for some other Hamiltonian which is similar to HF, but whose solutions you already know. Okay? Our solution is simple. So we try doing that. So this is, in some parlance it's also called as time independent perturbation theory. It's exactly what we are discussing. This is a very clear application of this time independent perturbation theory. We can basically just mean expanding in some small parameters. So first thing we have to do is identify what are the small parameters. If you don't know small parameters, you can't expand. So then you can't use perturbation theory. Fortunately, we have in our problem two small parameters. One parameter is theta 13, which we know is small. So you know theta 13 is smaller than 0.2. That's the parameter. That's a small enough. Second small parameter is a ratio of solar radiance per atmospheric radiance, which is this called alpha. So delta 2 divided by delta 31, and that's nearly 0.43. So knowing that we have two small parameters, what we will do is first we will put these two parameters equal to 0 and see what a Hamiltonian becomes. If the Hamiltonian is easily solvable, then we keep that as our H0. And then H1, which is the perturbative part, it's something that involves these two small parameters. So now what I will do is I will take this Hamiltonian, which we saw on this page. I simply put theta 1 is equal to 0 and I put theta 2 equal to 0. So calculation will involve multiplying 7 matrices, but I think we can. I'll show you the answer. Simplifying everything is again. The answer is surprisingly simple. The answer is just this. It's 3 by 3 matrix. Not only that, it looks like a very simple 3 by 3 matrix. Because its first row and first column have only one element, which is BC. And then this is a 2 by 2 part in the 2, 3 subset. So this matrix, this H0, looks eminently solvable. So if I ask you to calculate its eigenvalues and eigenvectors, you should be able to do that. Can someone tell me at least one of the eigenvectors? Maybe both. Yeah, so we got 1, 0, 0. Simple eigenvector is 1, 0, 0. What can the other eigenvectors be? You can look at this format of this 2 by 2 matrix here. No, not same. This is cos square, this is sin square. Oh, these are the same. It's a Hermitian matrix. Hamiltonian. Clearly not eigenvector. Those are the eigenvectors. 1, 1, 1, no. This is sin theta 2, 3 and cos theta. This is not normal. But you have to upload. I mean, this is basically, see, look at this 2 by 2 matrix. This exactly is what happens when you take something called 0, 1, rotate by theta 2. So eigenvectors here are going to be 1, 0, 0. So eigenvectors of this matrix is see, this was 2 sin square 3 delta 2 sin 2 3 cos 2 delta cos square sin 2 delta. So eigenvectors is basically one will be 1, 0, 0. The second one will look like 0 in cos 2, 3 and minus sin 2, 3. And probably different 0. Log value, sin. But this is just simple rotation. You see what has happened? If you look at this H0 matrix, this one H0, you will see that this doesn't have theta 1, 2, doesn't have theta 1, 3, only has theta 2, 3. So it's just one simple rotation. So theta 1, 3 is, of course, equal to 0, so it's not a surprise. The reason theta 1, 2 has disappeared is because we put delta 1, 2 equal to 0. Okay, this mass square difference. And as a result, this matrix has no. So we know that, okay, what are the eigenvalues? So we know eigenvectors. It should be easy for you now to guess what the eigenvalues are without actually solving. VC is 1, right? I think VC is 1. What are the other two? What is the determinant of this matrix?
VC times determinant of the matrix.
So what is the 0? Which is 0. So you know one eigenvalue. Which is 0. So for eigenvalues, we have got BC. Then you got a 0. What is the third one?
And place space.
Yeah, so add the
2 delta.
It's not difficult at all. It's only to convince you that we have got a Hamiltonian, which is those two actually Hamiltonian, which was complicated. Whose eigenvectors you could just find by inspection. We didn't have to solve the equations. So the idea is to find out such a Hamiltonian, which is what we use. So now our aim is the following. So you obtain firstly the eigenvalues epsilon j and bj eigenvectors to zeroth order, which we just did. We know what a zeroth order eigenvector is. And next thing we do is we do perturbative expansion in small parameters. So anyone remembers the time independent perturbation theory? Quantum mechanics 2 whatever course. So this is just this is something that we already solved, but I'll just give you some notation. So one standard notation is this definition. So BC divided by 2 times delta 31 is called as A hat, which is happens to be standard notation. So then this matrix H0 becomes simply like this. And then its eigenvalues that we saw were VC, 0 and delta 31. And they correspond to VC eigenvectors. So I have written epsilon 1 corresponding to V1, epsilon 2 corresponding to V2, and epsilon 3 corresponding to V3. So we should first start with this. Zero order things are. Now let me remind you of how to go to higher orders. So if you don't remember this, then you should go back and read your sample. So the first order correction to energy is simply Vj0 H1 Vj0. This is correction to epsilon G. Okay. Make sure notation is clear because different people do different notations, so I don't want to get confused. Okay, this is what. Second thing, we know how to calculate first order connections to Vj. What is that? You take Vj, you take its, you contract H1 with Vk, you divide by epsilon j minus epsilon k, and then you take multiply that by RDK. So whatever way you remember this is what. And add over all k not equal to g. So in general here what will happen is for V1 you will get correction due to V2 and V3. Similarly for the V2 will correction by V1 and V3. Okay. I'm not going to calculate this. I'm going to do this to you as an assignment. I just indicate you the procedure and then the details and calculations you should do because even if I do them here by putting some of my notes, nothing will go into it. Okay, just something. Right. So first order is this. The second order energy correction is simply this. I only go to second order because as far as this problem is concerned, you will not need more than that. So you might need epsilon j to second order, but you will not need Vj to second order. So therefore I did not write it. The expression is another way. And let's keep things as simple as possible. So everyone is familiar with this. So you have all the information. You know what are all the Vj zeros. You know what is H1 matrix, which you have to calculate. You have to multiply and you get humongous matrix. You have to do that. When you do these assignments, it's perfectly okay if you do it with mathematical numbers. You use any software analytical number to multiply matrix. I don't care. If you want to do it by hand on in a paper, even then I don't know. Just get some answer and so you know everything. You know what is epsilon j 0. These are all zero order things. So none of the eigenvalues. So I take it for granted that we have all done this. So you calculated the values of all the first order corrections to epsilon, all first order corrections to eigenvectors, and second order corrections to eigenvectors. So if we assume that we have done this, then what do we do? Our actual eigenvalue is then zeroth order eigenvalue plus first order correction plus second order correction. Okay. And my eigenvector is zeroth order eigenvector plus first order eigenvector. Okay, plus second order, but no, that's going to be used also on this way.
With parameters, lambda first order correction.
Yeah, so it depends on your notation. I work with lambda equal to 0. So you use the concept of lambda expansion by deriving these things. But once you do that, you can put lambda equal to 1. So if you are familiar with notation that uses lambda, use that.
Each one will contain a small.
Yeah. So here, by definition, H1 will involve sin theta only. H1 will involve delta 2. So H1 already has those form. So lambda is usually kept for bookkeeping to figure out which is what. Yeah, so use whichever notation you find convenient. If you have, if you are used to putting lambda squares, put lambda squares. That's the thing. Okay, so you have your eigenvalues, you have your eigenvectors. So we have to go one step further because only eigenvectors are not values. You need normalized eigenvectors. Because our aim is to calculate the mixing matrix Q. Therefore, we should normalize the eigenvectors. And then we put them in rows. So this is what we do. If you want to calculate the value of Q and dagger, you calculate this uj, which is normalized eigenvector Ej, and you put components of uj into a row. So this is u1n vector, u2n vector, u3n vector. So emphasize it again that u's are normalized. U3n are normalized. This involves this needs patience, but one can do that. Procedure is very good. And if you are using Mathematica, you just need some clever tricks to make it whatever you want to do. You can actually expand this more. Once you have this UM, then you can calculate everything, right? So UM star beta j, UM alpha j, and e power minus I epsilon j. Laksa m and then you have this equal. Okay. So this calculation is something that one should do once in one's lifetime. And if you keep good notes, then you can just keep it in one of your files. Because you need to look at it many times more. So once you do that, then I will use the probability of the instructor and just give you the answer. So let's see what the answer looks like. You will get this answer. So if you are patient enough and you do it well, not missing any factor, you will get this answer. It's very important to get this answer. Because if you don't get this answer, then something is missing. Go back and do your 900%. So this looks like they look like 4 terms, very long terms, but let's look at them carefully because they have some pattern. Let's see what the pattern is. So firstly, these are just notations which we already did. This is not a part of the solution. So alpha is delta 21 divided by delta 31. Then this delta, this is a state notation, but then we have to keep it. This delta is actually delta 31 times L. Just remember that there is an L also. This A hat is exactly what we had. So this quantity is the same as BC divided by delta 3. So now let's look at these 4 terms. The first thing to notice is what are the orders of these terms. What order are they? So the first term has sine square 2 theta 1. So let's say I take my small parameter to be equal to S13, sine of theta 1. Sine square 2 theta 13 means this is second order in theta 1. So first term is second order in theta 1. The second term has alpha. So its first order is alpha. And it has sine theta 1 3. So it is first order in alpha and first order in theta 1 3. So basically second order in small parameters. The third term is again alpha times sine 2 theta 1 3. So second order, again alpha times sine 2 theta 1 3. So second order is small parameters and alpha square is second order is 1. So all terms are second order is 1. Okay. Turns out that first order you get there is no term which is first order. That's a good. Now these terms get multiplied by factors and go on theta 2 3, theta 1 2 and so on, which are the order of term. Now let's look at the first term. The first term here is sine square 1 minus a hat delta divided by 1 minus a hat whole square. This should make you think of something. So it looks as if, see, this is basically sine square x by x square. Oh, okay, sine x by x. Yeah, sine x by x whole square. So you know what this looks like? Sine square, yeah, the delta here. So sine square ax by x.
So you can always multiply it by
Yeah. So this term is sine square of 1 minus e hat delta.
Sick is standard nomenclature.
Not exactly. You maybe sometimes remember what this sync was. It comes from certain parts of the vector. Yeah. So anyway, so you know what this looks like, right? This sin square x by x at x equal to 0, which is equal to 1, right? So it peaks here, and then near 0 is basically. So this tells you that this term is going to give you a structure that looks something similar to this. And this peak is going to be when a hat is equal to 1. So E at a hat equal to 1. So let's see what is a hat. A hat was BC divided by 2 times delta 0. This was equal to 1. So this basically means when BC was nearly equal to delta x square 3 1 divided by 2. So does this condition remind you of something? It's a resonance condition. Right? Our available resonance condition was BC is delta x square by 2e times cosine of 2 theta. Okay. But now note that we are talking about theta 1 3 now, and the approximation is theta 1 3 is close to 0. Therefore, cos theta 1 3 is nearly equal to 1. So these two are equivalent. In the theta 1 3 equal to 0. So the first term, this oscillating part of the first term, actually shows you that there is a resonance at theta 1 3 equal to 0. Sorry, at a hat equal to 1. So let's go back to this expression. So let's go to the limit when alpha is equal to 0. Let's see. Which means the last 3 terms will disappear. So you forget about alpha completely. So assume that there is no delta m square solution. Then the solution is simply the first line. Okay. And then it's very simple to see what happens. So this almost looks like the resonance at theta 1 3 0. In fact, if you combine these terms, sin square 2 theta 1 3 and this, it will look just like sin square theta 1 3 pattern. So, not exactly, but we'll see. It's some numbers. We have sin square theta 1 3. Then we had sin square of 1 minus a hat theta 1 minus a hat square. Okay. You can actually check that this is basically very similar, maybe with some factor, sin square theta 1 3 matter, okay, to Neutrino oscillations. Times, of course, there is some sin square approximately. So, therefore, vaguely speaking, one can think of the first term as the term into theta 1 3. That's what you observe. If you look at the last term, so last term is the term that survives when theta 1 3 equal to 0. Because theta 1 3 equal to 0, then first, second, and third term will disappear. Then you have something which is alpha squared. And again, it's alpha squared. It depends on sin square 2 theta 1 2 now, because the 1 2 is what works. And again, you get something that looks like a resonance. But that's not a resonance because a hat is a hat is not equal to 0. So the last term is simply oscillations with fixing angle theta 1 2. Sin square theta 1 2 times something. First term is simply sin square theta 2 theta 1 3 times some oscillation. Okay, so these are simply two stages of oscillation. Let me mention something more about this first term. Okay. So what this means is, okay, so let me put this condition like this. We see theta and square by. So what this means is, if you send neutrinos with different energies, for some range of energies, you will get a resonance. And see what is the idea of resonance was that even if you have very very small theta 1 3, at resonance you will always get significant oscillations. Second, you to remember, which I mentioned some time back, was if you get resonance for neutrinos, you will not get resonance for antineutrinons. That's always true because things go in opposite directions. If A is positive for neutrinos, it's negative for antineutrinos. So whenever you get resonance, it means A hat equal to 1. So A hat is positive. So therefore, for antineutrinos, A hat cannot be equal to 1. So now what I was supposing? So usually when theta 1 3 is very small, if you want to see oscillations with neutrinos and with antineutrinos and compare them, it's very difficult because theta 1 3 is very very small. Now you have an opportunity where you pass them to matter at certain energy. For neutrinos you get resonance, so you get very large oscillations. For antineutrinos you get very slow oscillations. So if you identify what the energy is, then you can say that at this energy, if the hierarchy is normal, I will get huge oscillations for neutrinos. Whereas at the same energy, if my hierarchy is inverted, I will get huge oscillations, but for antineutrinos. Okay. So in principle, this is a very simple way of finding out hierarchy. Of course, it would have been very easy if we had only the first term. Only first term would have been very easy. But we have the other four terms that will make things slightly complicated. Okay, so we will see how they are. So fine. So first and the last term is simply due to theta 1 3 and 2 1 3. Now look at the second and third term. So there are two features. One is, of course, they depend on both alpha and theta 1. Okay. And theta 1 3. What this means is that they are actually three neutrino terms. They involve three neutrino mixes. They involve neutrino 1 and neutrino 2 because you have alpha. They also involve neutrino number 3 because you have theta 1. So the first and the fourth term were basically two neutrino terms. They didn't really involve three neutrino. But these two involve both of them. Another thing you will notice is that this term has sine delta Cp, which is the same as phase delta, CPM matrix, PMNS matrix, and this has cosine delta Cp. So there was this Kobayashi-Maskawa result, right? That if you want to get Cp violation, you need a delta. To get a delta dependence, you need three neutrinos. So now these two terms, since they involve all three neutrinos, they involve delta. Yes, that's one thing. Therefore, these two terms depend on delta. Second thing is one of them is sine delta, other is cosine delta. And now remember what we saw earlier. If you want to see Cp violation, it only depends on this transform invariant. So let me define you what that is. So Cp violation depends on this transform invariant J, which was imaginary part of this matrix. This was simply sine 1 2, cos 1 2, sine 2 3, cos 2 3, sine 1 3, cos squared 1 3, and sine 3. So now, if we go back to the expression, and look at the second term, you will find sine 2 theta 1 2, which was sine 2 1 2 cos 1 2. This is sine 1 3 cos 1 3. Sorry, sine 2 3 cos 2 3. This is sine 1 3 cos 1 3. And then this is delta C. So the reason we don't see a cos 1 3 squared part here is because we have only taken care of the second order element. So this term therefore is the term that should give you singularity. Because this has sine delta. The second term, which has cos delta, is not giving singularity. It's a term that you can measure, but that is not singularity. Now these two terms, if you look, they look like interference of this and this term. See, this term has sine squared 1 minus a. This is sine squared a. Whereas these terms are sine a times sine 1 minus a. In fact, they are like interference terms. So one can look at these four terms as theta 1 3 term, alpha term, and two interference terms. One of these two interference terms is equivalent. So this has a pattern to it.
This cos is 131. There is cos delta C.
If you go from neutrino to anti-neutrino, what do? You change the sign of delta C. So you change sign of delta CP, cos delta C will approach. So now that we have this expression, okay, let's see some more features of this. This has some interest. So firstly, we go to anti-neutrinos. So what happens? When you go to anti-neutrinos, okay, we saw it before, right? All thetas stay the same. Okay, only the phases change sign. Which means only delta changes sign. Other phases we have already thrown out. So delta changes to minus delta. Then A hat becomes minus A hat because BC goes to minus BC. So therefore, the change is essentially before every A, you get a change of sign. And even here, this change of sign is because of this A hat. So this A hat should be minus A hat, so this changes sign.
Sine A.
Sine A hat. Let's see. So let me just write this sign. Oh, yeah, sorry. Delta C. Sine delta C. Yes. Because these signs. So then you put at the end of then you also have to read this blue line instead of that. So this is straightforward. So very clearly, these two terms. So what changes is, of course, these expressions change. So you would think that, oh, the probability actually has changed, even when delta C was not changed. Even this term has changed. This is what we talked about in the last class as the fake CP probability. So even if delta CP is 0, so forget about this term. If you look at only this term, you will still see that the probability for neutrinos is different than for antineutrino. But that's not what we want. We want to measure delta, which is the fundamental CP. So we should be able to extract that term. So this is P of mu bar mu bar. It's just this expression by these two replacements. Now, let's look at something else. If by some means we are able to choose our experiment such that sine of A delta, A hat delta equal to 0. Let's say we are able to do that. What happens? These three terms automatically become equal to 0. If they become equal to 0, we only have to fit for this term. Okay. And we saw that this term is very simple. Right? So, as we saw, the simplest way to determine hierarchy would be look at only this term and then look for neutrino, anti-neutrino. Neutrino you have large oscillations or small, and that will be what hierarchy is. So it's desirable to be able to suppress all these three terms. Turns out it is possible to suppress all these three terms if we can get sine of A at delta is equal to 0. So let's see what's possible. Of course, we can try to get anything, but it should be possible. So, what sine of A at delta is equal to 0. So what does this mean? So A hat was BC. So that's BC divided by 2 times delta 31. This delta is delta 31 times N. So we got this quantity. Sine of this, but delta 31 actually cancels out. So what we do is sine of now first at A equal to 0 is equal to 0. BC we have no control over. BC is GF times N. N is density of electrons inside the orb. So it's a fixed number that we have no control over. However, if we can choose N, N is our choice. Okay. So if we can make BC times N is equal to 2 pi or 4. It depends, your choice. 2 pi or 4 pi, 6 pi. Then you will satisfy this condition.
Parameterization, there will be large error in L. Design experiment for varying L.
Yeah, so you will take care that your change of your phase should be known to alpha accuracy as well. So this quantity therefore should be well known. Typically, when you build this experiment, you will have this quantity
This one will have more
nearly
uncertainty
1.
in BC. This one, in fact, if you do it carefully enough, might end up having more uncertainty in BC than L.
DC than there. In fact, this experiment is, so once you know Neutrino parameters, this can be used to figure out what DC is. People have proposals of using this for what's called an Earth nomogram. Determine density structure of the Earth by using this. Anyway, so to answer your question, see what BC times here to be of the order of 2 pi. Okay, so to be able to retain phase information, accuracy in the measurement of this should be much less than 2. So if you are able to measure this quantity, if you say 1%, it's okay. You get 1% accuracy also. You measure to 10%, then it's 10%. See, problem appears when oscillating terms have oscillations which are 100, 1000, and so on. Okay. Here we are talking about sine of BCN by 2 equal to 2 pi. It's one oscillation. So with one oscillation, then if you can resolve into energy bins, so that you can take 10 energy bins, you are safe. Coherence will not be lost. So what's important here is that this condition does not depend on energy. So, crucial part of the argument is the following. So any energies you want, you just choose the right, so you know what is VC, because you can calculate what is VC, you know what is approximately. You can calculate N. This N turns out to be about 7,000 kilometers. If you want to keep to 2 pi. If you want to go to 4 pi, it goes 14,000, which is not possible in Neutrino. So you only look at 7. So what this means is the following. It's a very simple answer, right? So this implies that if you make an experiment where the distance between your detector and source is about 7,000 kilometers, then these 3 terms will not matter. You only have to look at the first term. And if you look at the first term, then you know mass error. Because this is exactly what it is. So if you want to know mass hierarchy, without having to have contamination because of circulating phase, it's good to go to what's called as magic phase. It's called magic because it's not dependent on energy. This was unexpected result. So people do that. So this channel, this PEU, is actually what's called as golden channel. It's called golden channel. I tell you why golden. Golden is because if you can prepare initial state well, and if you can detect the final state well, it's a golden channel. For detection, mu is very easy. And for initial flux, mu or mu is okay. So in that sense, this E to mu is called as the golden channel. And also, as we saw, the probability expression itself gives us handle on many things. So this is supposed to be okay. Then the channel, if you want to look at E going to tau, you can create things well, but detection is slightly hard. That was called as silver channel. Okay, this is just notation. If you go to E tau, all you need to do is, wherever you are sine square 2, 3, change to cosine square 2. Okay. So here you get sine square, but here you get sine square. If you go to E tau, you will get cosine square. Similarly, here is cos square becomes sine square. This was sine 2 theta 2, 3, so that doesn't matter. Sine and cos. Again, these are the sign changes. So you get is green minus signs here and here, and you get these interchanges inside these green boxes. So this is just a good slide to have, which tells you expressions for many things. Then there is this channel called as platinum channel, which is basically not P mu but P mu. It's called platinum channel, especially because I will talk in a few minutes. This was in the context of what are called as Neutrino factories, which produce very intense muon beams. It makes it very easy to make a mu beam. So you make a mu beam, you detect mu, take mu, which is not too hard. So it is also called platinum channel. So if you are look at E mu and P mu E, then also you can see what happens when delta C goes to minus delta C. So all these mu minus signs have come because I have made P mu E and not E. So remember, they are not the same. If you make mu E and find mu, the probability is different than what you will get if you make mu and detect mu. It's different because you have this phase delta C. If delta C was not there, P mu is equal to P mu. Because then delta C is not there. So this is different. So platinum is different from anti-neutrinos because in anti-neutrinos A goes to minus A. But here it's only delta C that goes to minus A.
Basically, what is the thing that if you are looking at probability of mu going to E and E going to mu, the delta C becomes
Question is, why should that be the same? Get some arguments for.
no, but why the delta C become
Why only delta C changes?
or is this
I can-
just
I can-
disorder or something?
No, I can mention again. See, this comes from your brackets, your bracket alpha, beta, ig. When you interchange alpha, beta, this U element with interchange. Maybe star goes on some other elements, therefore beta something. That's so this is sort of a good master slide you had in front of you if you want to think about various possibilities. However, this only shows E mu kind of things, change of. So it's what I call as appearance experiment. It's a if you make mu and look at mu again, they are disappearance experiments. Okay, so people talk about those also. You can calculate that also. So yeah, so you need to stare at this for long times. At some point of time, yeah, we will start thinking in terms of these four terms. We are dealing with so this was theory. Okay. So now let's see practically what can we do with this. So firstly, all this thing that we did is useful when VC and delta 3-1 are of the same order. If VC is very small, you forget about it. When you only talk about delta 3-1, it's like vacuum oscillations. So you don't know. We know what VC is inside of it. It's nearly 10 power minus 13 electron volts. No density of course, so this quantity is very, very, you can get perfect. Which between 10 power minus 13 to 10 power minus 12 electron volts. So this is one condition. So delta 3-1 should be 10 power minus 13 electron volts. So delta 3-1, so VC is 10 power minus 13 electron. So delta 3-1 is 10 power minus 13 electron. So this is delta L square 3-1 divided by 4E. So this is 10 power minus 13 electron. Okay. So now let's see what energy is. Energy correspond to delta L square 3-1 divided by 4 times 10 power minus 3. Delta L square 3-1 is 2.5 times 10 power minus 3 divided by 4 times 10 power minus 13 electron. So, 10. So, 10. So, this tells you that if you want to do such an experiment, where you will get all these hierarchy and data set and so on, you will need to do the experiment at energies which are around 10 G. So, without doing anything, just by doing these estimations, we know that our experiment has to be at 10 G, near. Next, energy should be 1 to 10 G. Now, what we want is that these probabilities, it should be significant. So, if you want oscillations, oscillation should have been at least completed pi by 2 or pi. So, this quantity should be of the order of pi, sin delta. If your delta is very small, if your length is very small, your delta 3-1 times L is very small, and then this term is going to be, all terms are going to be very small. Everything depends on sine square of L. So what we want is that your delta 3-1 times L should be of the order of 1, not very small. So this means if delta 3-1 was, so actually you know something more, right? You know this oscillation, you know, it has sine square of 1.27 delta L square in by kilometers electron volt and so on. So this is 1.27. Delta L square is some 2.5 times 10 power minus 3 electron volts. E is 10 GeV. We want this term to be of the order of 1. So let's see. So 1.27 times 2.5 times 10 power minus 3 times L in kilometers divided by 10 should be of the order of 1. So this tells you that L should be of the order of this thing, few times 1000 kilometers. Actually, this L comes out to be some 3000 to 4000 So few times 1000. So this is a general idea. So therefore, if you want to do an experiment, it's essential that your energy should be of the order of 10 GeV and length should be of the order of 1000 kV. These are what are called a long baseline experiments. So all the long baseline experiments, therefore, will have energy of the order of 10 GeV and length of the order of 1000 kV. That is the work of. So let's look at what kind of long baseline experiments we have in the pipeline. There are mainly three kinds. The first kind is called as super beam experiments. What super beam means is standard conventional beam. So you have a target, you accelerate protons, hit target with protons. When hit target with protons, you just produce lots of random particles. You get pions, you get kaons, you get delta particles. So, but mainly you get pions and kaons because they are very light. Pions and kaons decay, and in decay they make neutrinos. So what you do is you let pions and kaons travel through some beamline. After some time they will decay. Either they will decay or they will react with some other thing that is happening. What will left is neutrinos. That gives you a neutrino beam. So super beam is in some sense the most naive way of making the neutrino beam. It's also good because people have been making such beams for decades, so they are used to this. So technology is very, very good. This is the super beam. Okay, super beam is again also called as conventional beam. Okay. So super beam is also what's called as conventional. Typically, the fluxes look like this. So forget about this. So this is some super beam created. This is at Human National Lab. Heating protons on graphite. That's the heat. So you get a new flux like this, and you get a new flux. So normally what you do is the following. So you produce lots of ions and kaons, and you apply magnetic field. You apply magnetic field, you only take out negative ions. So you only get mu and mu. So you can do it. Therefore, a beam of super beam usually consists of mu and mu. And typically, mu is about 1% of mu. Now, what do you want to see finally? You want to see, let's say, P mu E. So you want to finally take electron neutrinos. So you detect some electron neutrinos, but there is a problem. You will not know whether they came from this mu or this mu. What is the experiment? So forget about it mu further. I create a flux of mu that looks like this. I go far away and detect what I see. I want to see the probability that this is what I want to see. I want to see probability of mu going to mu. That's my aim. This I have a detector which detects mu. So if this contamination was not there, I would just see what is the mu observed and I make all the measurements. However, there is this background of mu, which is problematic because this is about 1%. With this probability, if I want it to an accuracy of 1%, I cannot trust my measurements. It could have come from this, or it could have come from this mu, which never oscillated. So therefore, advantage of super beam experiment is that it's easy to make. Disadvantage is if you want accuracy of more than 1%, you can do nothing. Because there is no way to remove this background, this contamination of fluid. It is called as the beam background. is the low moment, and known technology is the high one. So in fact, this experiment T2K, which is already started in Japan, is a conventional experiment. In fact, all the experiments that are there currently are conventional experiments. Super. Okay. The experiment is Minos, is a conventional experiment. So is this. Everything we talked about earlier, we talked about this K2K earlier, that is Perturbatively. It's a conventional experiment. Super. So people now just try to give the intensity of super beam and so this is positive part and this is negative. This is the negative. Then we go to Neutrino factor.
The one thing we can do, the near experiment we can take that, and after some distance we can make it. And taking the ratio near the source and taking the ratio after some distance, we can.
So people in fact also try to do that. So that is one way of reducing this backup.
Yeah.
So in spite of that, turns out that there are certain uncertainties that cannot. So the issue is not as bad as this, and some improvement about this. T2K, for example, has detected goes by. The Neutrino factor is a very different problem. Here you don't have K1s or pi. You only take muons. Okay. So this is not very clear. The principle is very simple. So you first make muons. So that you can make by making pions, making them decay, make muons. Okay. But before muons decay, you have to accelerate them to very high energies. So you accelerate them to muon have mass of about 100 MeV. Accelerate them to about 10 G, gamma factor of about 100, maybe 50 G. So now they need longer. Once you know accelerate them, then you put them inside a long pipe. So they decay along this line. So 50 GeV muons would mean lifetime has increased the factor of 100. Okay, 500. So which means 2.2 microseconds become milliseconds. So you make this pipe so that neutrinos then decay along this line, muons decay along this line. The neutrinos then travel through the Earth long distance, okay, and then you have a detector. Okay. So this is actually a detector of a kind similar to iron. This is a approach detector. And this will have iron plates and magnetic field as well. Okay. Now what happens in Neutrino factory is the following. So if you look at just the first spectrum, this is the spectrum of 2E. These three curves are from three different energies: 5 GeV, 12 GeV, and 25 GeV initial muon. So let's just look at initial mu minus. Okay. What does mu minus give me? Mu minus E minus plus Q plus mu E bar. So you get mu and you get mu E bar. So now the new mu spectrum will look like this. Let's take this 25 GeV thing, the largest index. So mu flux is this, okay, up to 25 GeV. If you have configuration, you do mu bar flux. But mu bar flux, this is mu. It looks like this. So almost of similar kind. Magnitude is almost same.
These are detected.
No, these are produced fluxes. This is produced for this is actually mu. This is mu bar. This is mu bar. This is mu. So if I make muons decay, mu minus, I will get this and this flux. if I have U plus decay, I get these two fluxes. Top two fluxes. Now you see that we at least get mu and mu bar of nearly the same magnitude. However, the good thing is that one is a neutrino, other is anti-neutrino. Okay. So therefore, if this mu converts to mu e, okay, this mu e in the detector will give you an electron. However, this mu e bar, if it comes to the detector directly, it will give you a positive. So although it looks like both of these are mixed fluxes, mu e and mu, if the detector is capable of resolving positive muons or negative muons, or positive electrons or negative electrons, this is not a contamination at all. In fact, it's good. Because then you have a detector which can detect both mu and mu at the same time. Electron and muon distinction is trivial. In a ion kind of detector, just by looking at the distance the particle travels, muon will travel much longer, electron will travel only short distance. So E and mu separation is very easy, just by looking at distance travel. Muon will travel meters, electron will travel centimeters. So that is easy. This allows us to separate also electrons, so muon from anti-muon, for example. This means you can identify whether you got a mu or mu. Now, if you got a mu here, you know that they came from this this spectrum. If you see a mu bar here, you know that it came from this spectrum. So, in one go, therefore, if you have minus negative muon, you can therefore determine E mu and E. It should take muons. E bar mu bar. So when you take muons, positive muons will tell you about P E bar mu bar. Negative muons will tell you about P mu. So it's 2 in 1. So therefore, neutral factor is useful because it's useful if you have a detector which can distinguish between positive and negative. So, and once you do that, then you have more advantage over supervision. If you want to go to accuracy of more than 1%, then you need neutral factors. Because neutral factors basically have no inherent limitation. So although the technology is harder, because what you need to do is you want to make muons, you want to accelerate muons, and you want to focus muons. Let's say you want to send a beam to a place which is 1000 kilometers away. Now, if your beam width, if your beam is so wide, by the time it's 1000 kilometers away, it will occupy some radius of 1000 kilometers, which you don't want. You want it to occupy this radius of maybe 10 meters. Therefore, the beam needs to be really focused, not about micro radius. So, focusing of muon beam is the main problem with muon storage. So, this technology is still being developed. So, when people talk about neutral factories, they talk about something that will happen maybe 25 years before. Because when you develop technology, then build the detector and then make something. This is long term. So last part is this thing called as beta beam. See, what is the idea? The aim is to have as much clean beam as possible. We shall produce it as clean as possible. Super beam was kind of dirty. Beta beam, nuclear factory was cleaner because you had the detector to separate the two. First cleaner version is beta beam. Beta beam is you take nuclei which undergo beta decay. Okay. And we know that if you have beta decay, you can only get electron positive. That's it. There is no contamination. So this is in some sense a very clean beam. So people have identified some nuclei which have reasonable lifetime, so 2 seconds and 1 second, and reasonable energies. So of course these energies are energy in the range frame, boost them, accelerate them, and then you can. So this will give you the new E. This will give you the E bar. I think so. And then we accelerate these. So accelerate ions. Okay. Not accelerate neutrinos.
But the flux of these neutrino is very low.
So yeah. So you need to first collect lots of ions. Okay. Again, combine them, take them, make them into bunches, and accelerate them. This is the technology which people are trying to develop. This is again something which is not now, but 15 to 20 years in future. So you make these ions, you collect them, accelerate them, and you do all these things before they leak. You don't have much time. So you take these ions, you pass them through these linear accelerators, then through synchrotron accelerators, and make this thing. So this is in some sense a clean beam. So the two good sources that I use are this 6 helium and 18 neon, which is what I showed you here. Helium and neon. Okay. You can give them energies of the order of GeV, because that's what you want. Okay. And this is a typical spectrum that you will get for neutrino example. So again, T of the order of it is 2 GeV. In principle, you can make it larger, it will be larger as well. So this is going from a slightly dirtier but easier source to cleaner source. So if this happens, this is what we are going to do. So this is just some futuristic thing. So SPL is what we have currently. This is small axle. This is T2HK, which is Tokai to hyperconductor. Hyperconductor is the futuristic detector of 1 megaton. So this is conventional. I don't know what is WTP. NFE neutrino factory. BB is better. So this shows you how well you can measure certain parameters. So this tells you how well you can measure theta 1 3. So this means that if you go to a neutrino factory, this is some data CP fractions. Forget about that. It tells you that if you go to a neutrino factory, you can detect theta 1 3, even if it is as low as 10 power minus 5. Sin square theta 1 3 is less than 10 power minus 5. So right now we are somewhere here. Sin square theta 1 3 of the order of 10 power minus 3. But in the next 20 years, we can do 10 power minus 5. So you basically improve by 2 orders of magnitude. This is again measurement of mass ordering, hierarchy measurements. If the theta 1 3 is small, then measurement of hierarchy is very difficult. But now if you do neutrino factory, for example, you can determine hierarchy even when theta 1 3 is as low as 10 power minus 4, 10 power minus 4. Right now we are here. So I know, for example, we will be able to detect hierarchy only if theta 1 3 is somewhere here. Not very far. It's like deep waste, somewhere this. But a neutrino factory can even go to this much.
But the neutrino factory is the source. I know the detectors. What does it mean when you say that?
Oh, when I say I know, I mean I know phase 1, atmospheric only. If you use it as a detector for a neutrino factory, then yes, then you go ahead. And this is, for example, if you want to measure delta CP. Again, if you want to measure delta CP, right now we are somewhere here. We have not measured delta CP at all. But then if you have neutrino factory, you can measure delta CP even when theta sin square theta 2 3, sin square theta 1 3 is about 10 power. So the aim of building all these long experiments is able to improve the sensitivity to various parameters by factors of 2 to the content. Are ambitious aims, therefore take 10 years, 15 years. Okay, so you should not be worried that you have nothing to do after doing a PhD. These experiments, if R&D is still going on, it will still take about at least 15 years to be updated. So you might be involved in building of some of these experiments. Yeah, so I will stop here. and then we'll meet directly on next Monday.